So teacher, does this effect explain why the swing stops when playing at the playground?
Wow, that's a good question. So you want to know why? Let's learn together. Hello and hi students! Today we are going to continue our lesson on chapter 5 on subtopic 5.2 Damping and Resonance. I hope at the end of this video you are able to describe damping and resonance for an oscillating or vibrating system and able to justify the effect of resonance in our daily lives. So let's get started. So what is damping? Well, damping is an oscillation with its amplitude decreasing with time, and the system will gradually lose energy in the form of heat, which resulting the oscillations to stop. So now let's observe the phenomenon of damping in an oscillating system such as a simple pendulum, and we can sketch an amplitude as time graph as shown. Now we can see that the amplitude of the oscillation decreases with time. Well, to make it easy to understand, damping is the reduction in amplitude in an oscillating system due to the loss of energy. And during damping, the oscillating frequency remains constant while the oscillating amplitude decreases. Next, the oscillating system experience loss of energy is due to the external damping and internal damping. External damping is where an oscillating system loses energy to the extension or compression of the molecules in the system, while internal damping is where an oscillating system loses energy to overcome frictional force or air resistance that act on it.
Well, the oscillation of a simple pendulum experiences significant external damping but insignificant internal damping. For the vibration of a spring, both external and internal damping happen significantly.
Are you guys still with me? Now let's try to answer the question related to our topic.
Now, let's answer the true or false question. Damping is the reduction in amplitude in an oscillating system due to loss of energy. True or false? The answer is true. Good. So now, let's continue our lesson.
Why the guitar string slowly stops and then produce sound.
So now, let's continue with the demonstration of oscillating pendulum to see the effect of resonance.
So now, we are going to observe a demonstration of Barton's pendulum. In this video, there are 6 pendulums which are A, B, C, D, E, and F, and each of the 2 pendulums has the same length. The demonstrator began to oscillate the longest pendulum. Let's observe together. Now we can see that the oscillation of the longest pendulum transfers energy to all pendulums, causing them to oscillate. Resonance happens to a pendulum that has the same length as pendulum A. Because pendulum F has the same natural frequency as pendulum A, the pendulum oscillates with the largest amplitude. The steps are repeated with different lengths of pendulum, and let's observe the effect of resonance on each pendulum together. So, when second pendulum oscillating, it transfers energy to all pendulum and causing them to oscillate. We can see the fifth pendulum oscillate with the highest amplitude because it has the same length and thus it has natural frequency as second pendulum.
Well, resonance happens due to the oscillating system that vibrates equally to its natural frequency. What is natural frequency? Well, natural frequency is an oscillating system that is displaced and then left to oscillate without any action of external forces. So now let's move on to the effect of resonance in our daily life. For example, guitar. A vibrating object causes a sound wave. When a guitar string vibrates, it creates vibration that ripple in and out of contact with surrounding molecules. This frequency corresponds to the guitar string's vibration frequency. This is when the effects of resonance can be observed during picking up the guitar, with each string vibrates equally to its natural frequency. Thus, this vibration produces the sound of a guitar. Next is microwave. Are you sure, teacher? Well, the food is heated quickly in microwave because of resonance. The radiation emitted by a microwave oven have a certain wavelength and frequency, and like all other objects, molecules of water and fat also have a resonance frequency. At a certain frequency, the molecules absorb wavelengths and start vibrating, causing cooking and heating up of food. And lastly, radio. When we turn the knob of the radio to our favorite channel, we are changing the natural frequency of receiver. The natural frequency of the receiver then matches the transmission frequency of the radio station. When two frequencies match, energy transfer occurs, and we listen to the selected channel.
Hi everyone, now you are in segment Let's Explore with Teacher Anis. Okay, so now what we are going to do is, to understand about resonance better, we are going to do some activity that you can do it at your home. So, material needed for this segment is 3 sizes of empty water bottle. So the first one is So the instruction is, you need to open all the water bottle and make sure the water bottle is empty. Resonance. What you need to do is to blow on the top of the water bottle. And let's observe. So the second bottle. The third bottle. So did you hear that? So what is actually happened? When you blow across the top of an empty bottle, the air inside the bottle vibrates. This is because the air is being forced to move by the stream of air you are blowing across the top of the bottle. The frequency at which the air vibrates depends on the length of the air column inside the bottle. Well, the air column inside the bottle is like a closed-end pipe. A closed-end pipe is a pipe that is closed at the end and the other pipe is open. When the air is forced to vibrate inside a closed-end pipe, it vibrates at a specific frequency, or we call it as natural frequency. Okay? So, the natural frequency of a closed-end pipe is determined by the length of a pipe. The longer the pipe, the lower the resonance of the frequency. This is because the air has to travel a longer distance inside the pipe to complete one vibration. And the smaller the pipe, the higher the natural frequency. When you blow across the top of an empty bottle, you are essentially forcing the air inside the bottle to vibrate at its natural frequency. This causes the bottle to resonate and make a sound. So, the pitch of the sound that the bottle makes, it depends on the natural frequency of the bottle. The higher the natural frequency, the higher the pitch of the sound. Well, this is because the higher the frequency, the faster the air is vibrating. Well, that's all from this segment. Goodbye! So now, let's try this following question by choosing the correct answer. Which of the following are not the example of resonance in our daily life? So the answer is yes, true.
Awesome!
Now, let's answer the summative practice together. The answer for question 1 is damping is an oscillation with its amplitude decreasing with time, which the system gradually lost energy in the form of heat and resulting the oscillation to stop. Next, to sketch a graph of displacement against time for a system experiencing damping, first we're going to draw the axis, then we draw the graph. And we can see that the energy and the amplitude decreases, but period of oscillation and frequency remain unchanged. The last question is state 3 examples of the effects of resonance in our daily lives. So the answer is radio, guitar, and microwave. Good job, everyone! So we are at the end of our lesson. These are the value learned from this topic. So the first value is damping and resonance are two important concepts in physics that have many applications in our life. And the second value is by understanding these concepts, we can better understand the world around us and the things that we use every day. Lastly is the importance of balance. The right amount of damping allows an object to resonate without causing damage. Well, that's all from me. See you guys in the next class.
So now you are already able to describe damping and resonance for an oscillating or vibrating system and to justify the effects of resonance in our daily lives. Well, that's all from me. See you in the next lesson. Goodbye.